Today I wanted to give an overview and an explanation of Godot's Transform3D and basis types. These are going to be used all over in 3D game development, and you're definitely going to need to use it if you're creating a 3D character movement script. So in most 3D character movement scripts, you'll probably see a collection of lines that look something like this, where we first get the input direction vector. And then on the next line there, we're basically multiplying it with the transform.basis of the character body. And put simply, this is going to rotate the input vector so it's relative to the character. Then we have a desired movement direction, and you can multiply that with the character's move speed. And that'll set the character's velocity to move in the world direction that we want. And here's just a quick visual of the input.getVector function, which basically just maps your movement keys, whatever you assign them to a vector, so you can easily go from user input to a vector in whatever direction you want to move. And then multiplying it by the basis basically takes it from that pure XY vector to a vector that's going to be relative to the character body. And we also move it to 3D. Instead of X and Y, we set Y to 0 and map Y to Z because we want it to move horizontally in this 3D world based on 2D controller or keyboard input. And to illustrate, if I remove this transform.basis multiplication and I try to go forward, you'll see the input is no longer rotated as relative to my character's forward-looking direction. It's just whatever the forward direction of the world is. So whether you know it or not, if you're working with anything 3D in Godot, you're using Transform3Ds pretty much all the time. They are what encompass and store the position, rotation, and scale of every 3D object, and they're also what enable children of nodes to move relative and along with their parents. So I think it's a pretty intuitive concept, just having children grouped with their parents so they move relative to them. But it's important to understand what's actually happening here is that when we get the position of a child to render it or do pretty much anything in game, we multiply up the tree the child's local transform with all of its preceding parents' transforms up the tree, as many nodes as it has parents. So here's an example where we have a point or a sphere in front of our player 1. And right now the sphere's local and global position are in the same spot because the player is just centered around 0, 0, 0, the origin. If we move our player, our point's global position is going to change, but it's still going to stay in the same local position relative to player 1. So as an exercise here, if I want to do what Godot basically does for us all the time and go from the point's local position to get its global position, I can multiply its parent's transform by it, and that will transform it from local space to global space. And you can see I've printed out the transform here. And that last part there, referred to as the origin, is the position of the object. So transforms usually enable us to go from local to global space, but you can also use them to go the other way, from global space relative to any other transform. And to do that, you can use the inverse of any object's transform. You can see here I'm multiplying player 2's transform.inverse multiplied by the point's global position, and we get this 4.4, 1.9, 2.9, and we can verify that is right by using Godot's built-in reparent function, and this is going to keep it in the exact same global position but make it relative or parented to player 2. And now you can see our previous calculation is correct, where we made the point's global position relative to player 2. And of course there's a global transform property for all node 3Ds. You don't actually have to multiply all the way up the tree. That's just how it is ultimately calculated. This would just give you the same result as if you had multiplied all the way up the tree in a chain of all the parent transforms of any node. One thing to note, taking a look at the Godot documentation of Transform3D, there's actually two inverse functions. There's affine inverse and regular inverse. So what do these two do? Basically, the regular inverse function only inverts the position and rotation, and the affine inverse inverses everything. So if you're trying to find the inverse of a node that's scaled in any way, the regular inverse isn't going to work. You can see when we take the inverse of a transform that's scaled up by 2, it just gives us the same transform, which is wrong. The inverse of scaling something up by 2 would be scaling it down by 2 or scaling it by 0.5, and you can see we get the right value if we use the affine inverse function. When I was first learning about transform3Ds in Godot, I got confused about the difference between these two functions, but you can see the docs. It says the basis has to be orthonormal, which basically just means no scale or skewing is allowed. And you can see in the Godot source code here, these are the functions that deal with it if you're curious. And you can see the invert function that the regular inverse uses. It just transposes the basis, which just inverts the rotation, and it inverts the origin too. So it's only dealing with rotation and position. So scale won't be inverted. So don't worry if you don't understand all this yet. I'm just trying to give a basic overview of how transform3Ds are used in practice, and to give you some useful tools in your toolbox for 3D programming in games. So every transform3D has a basis and an origin property. The origin is going to be the exact same thing as taking the object's position. And the basis is what encompasses the scale and rotation of the object. Taking a look at the basis documentation page, you'll see it says it's a 3x3 matrix used for representing rotation and scale. And basically what that means is the same way a transform encompasses the position, rotation, and scale, and you can multiply a transform by any vector or other transform to apply that transform's position, rotation, and scale, while multiplying by a transform.basis will only apply rotation and scale and not position. So you'll see a basis has 3 properties, x, y, and z, and they're each vector 3s. And now these are the columns of the 3x3 matrix, but that might seem a bit abstract if you haven't worked with matrices and you haven't seen the visual reference of what that actually looks like. So back in Godot, here is the visualization I've made for a basis. And this is displaying or visualizing this character, player 1's transform.basis. The 3 arrows are the 3 x, y, and z properties of the character's transform.basis. And you'll see essentially what a basis is these 3 vectors or arrows that are going to be pointing always in the same relative up, right, or forward directions relative to your character or whatever object that you're getting the basis of. And it might depend on your character model whether positive or negative z is forward. But it's the relative x, y, or z directions to your character. And so I think just knowing this is pretty powerful and useful to know that you can always get these relative x, y, or z vectors to any character or object in your scene. So what might you actually use this for in your game? Well, say for instance you wanted to spawn an item 2 spaces in front of your character. Well, then you can just add player.position plus the basis vector multiplied by however many spaces you want the item to be in front of that character. So here I want a grenade to spawn 2 spaces in front of my character, so I multiplied the basis.z times 2 and added it to the player's position. And if instead of in front of your character you wanted it to the side, you could use the x basis, or above, that would be the y basis, and so on. And I want to talk a bit about the math involved in transform3Ds. And while I think it is absolutely not necessary to know all the underlying math to use transform3Ds, it is useful to know, and it is empowering, and it will help you be a better programmer and game developer, and it's just really cool. So I want to talk a bit about the math. So like the Godot docs say, the transform3D is a 3x4 matrix, which is 3 rows and 4 columns. And these basis.x, y, and z vectors that I have visualized out here on the little axis grid that I created, they are quite literally the values of the columns of the matrix, as if you were, in math class, you were doing matrix multiplications by hand. the x, y, and z basis vectors are going to go into the first three columns of the matrix. The fourth column of the matrix is for the position of the object, also referred to as the transform's origin. It means the same thing. And so if we want to write out the exact value of this matrix by hand, what I'm doing here is just copying over the values you see on the right next to the axes, which is the basis.x, y, and z values, and this is how it would look in matrix form. And I don't have the position of the character on hand here, so we'll just say he's at 0, 0, 0, which would be, if he was at his spawn point, that would be true. And if you've never used matrices before, you might find that interesting, and hopefully you might be feeling like maybe matrices aren't this scary black box of mystery, and that they actually have some rhyme and reason to them. And so before we continue talking about matrices, I want to do a really quick review on what a vector actually is. And so a vector 2 at least is going to be two components, x and y. The x component says how far along the x-axis the vector goes, while the y component says how far along the y-axis it goes. And more commonly, you'll probably see them drawn as arrows, which land at the sum of the x and y components. When we scale a vector by a number, each of the x and y components gets scaled by that value or multiplied by that value, as well as the total length of the vector is scaled by that much as well. If you have two vectors and you want to add them, that is as simple as adding their x components up individually and then their y components up individually, and then the results of each of those is the resulting vector's xy values. And spatially, what's actually happening there is that would be the equivalent of putting the two vectors' arrows end to end and seeing where the final arrow ends up. And for subtracting them, a common use case would be, for instance, if you want to get one character's position relative to another character, you could subtract the first character's position from the second, and that would give you a vector representing the first character's distance in the x and y directions towards the second. Kind of like an instruction of how to get to the second character relative to the first. Alright, so next I have this web demo that I've created, and this basically shows a point that rotates relative to a plane. So this would be just like in Godot if the point was a child of the plane. And now the question I'm asking here with this is, how do we find the position of the point given the rotation of the plane? Without actually having it enabled and seeing the exact position on the screen. We know it's always at the position 2, 1 local to the plane, but when we rotate it, say we rotated it right here or so, we can try to count exactly where it is. Looks like it's a little under 2 on the x and a little over 1 on the y, but it's anyone's guess exactly where that point lies. But another way to look at it is that it's still at the point 2, 1, but it's just on a grid that is relative to and follows this plane. And so no matter where we rotate this plane, the point is going to stay at the exact same local position on this plane's local grid. And this is kind of like when a node is a parent of another node in Godot. Actually, it's exactly like that. It has this separate transform space, which uses its parent's transform to position all of the child nodes. And even if we scale up the parent, say we're stretching this plane on the x-axis or stretching it on the y-axis, the point is still at 2, 1 on its parent's transform grid, but the grid lines themselves have been stretched. And also the basis vectors have been stretched. So this is just like in Godot, like we saw earlier, where we have the transform basis x and transform basis y values. And these are the relative x and y directions in this plane's transform space. And they're always going to follow along and change with the plane. And so hopefully it's clear, no matter where we rotate it, we can always find the position of the point on the primary grid here, just as we were finding the position of the grenades I spawned earlier, or the position of the original sphere or point that was in front of our character before. So in this case, because the point is at the position 2, 1, that would be 2 times the x basis plus 1 times the y basis. And this would just be the simple vector multiplication and addition, which we learned earlier. And no matter where the point is, it's going to remain as a composition of the parent's 2 basis vectors. And we can always find the location of the point on the primary grid using that tactic. So if I do the math by hand here, I'll take the x of the point, which is 2, and multiply it by the x basis, which is 0.7, negative 0.7. That'll get us 1.4 and negative 1.4. And I'll do the same with the y basis here. It would be 1 times the y basis, which is just the y basis. Add them up with our standard vector addition, which remember is the equivalent to putting the vectors end to end, and we get 2.1, negative 0.7. And if we enable the world position of the point, you'll see we calculated the exact correct value using the parent's basis vectors. And actually what we just did right there, that calculation, is exactly equivalent to a matrix multiplication. That is, we just did it manually by hand, what a matrix by vector multiplication would look like. So the position of the point multiplied by that matrix, or the transform composed of those 2 basis vectors, gives us the transformed value of the point. And in fact, that is exactly how it works in Godot as well. For every vertex on your screen, I mean, this is a 2D version, but it's the same concept done in 3D. So when you're rotating or scaling an object, what's really happening is you're rotating or scaling these basis vectors. And when the transform multiplication is done, every vertex or object will be transformed to this rotated and or scaled space. So have a look at these 2 basis vectors right here, 0.7, negative 0.7, and 0.7, 0.7. And now I've moved over to Godot to show a little demo here. I have the exact same setup. I have a point which is rotating around an axis basically. And the point's position is at 2, 1, just like our web demo over there. And now if I select the parent of the point and come over here to the Node 3D's Transform tab, and if you notice it has a rotation edit mode property, you can set that to basis. And now if I go and set these values to the exact same values as our graph, I've done just that, and you'll notice the point ends up lying in the exact same location as it does on our graph. And this is of course because Godot and really every 3D engine uses matrices for object transforms under the hood, and we've gone and set the basis matrix, the 3x3 matrix, which represents rotation and scale, to the exact same values as we had in our web demo. And hopefully it's clear how this 2D version maps onto the 3D space in Godot. Here's this initial example again with the point relative to the player. It's 2 in the z direction, 1 in the x direction, and 1 in the y direction. Point's position is 1, 1, 2. So if we draw the arrows before, just like on our 2D graph, you'll see that the sum of the arrows, which are made up of the basis vectors of the graph, will get us the exact position of the point if we were to add them. And of course this is relative to the player's position as the starting point. And here I have a very similar setup to what I just showed you, but in code. And I have this example where I'm basically manually doing the transform multiplication. And I have one example here where I use Godot's built-in Transform3D type, And then here I also show the equivalent of what that looks like manually written out, which is basically what we just did. So if we have a situation like this, where we have a character that's rotated 45 degrees to the right, here I'm setting up the X, Y, and Z basis vectors, or the right, up, and forward vectors for the character that we can use for the basis. Just creating the X, Y, and Z vectors and then rotating them 45 degrees. And then we have our character position, the points position, and you can set up a Transform3D manually by placing the X, Y, and Z basis vectors, or just a basis as the first argument, and then the last argument is the position of the transform, or its origin. And then if we run the matrix multiplication, so you can multiply a Transform3D by any vector, and that's going to be equivalent to putting that point into its own transform space. And then here I have the exact same logic that we just did, which is adding all the vectors and putting them end to end, which is all the visuals we just showed, but I'm doing it here in code, so multiplying the right, up, and forward, or the X, Y, and Z basis vectors by the point X, Y, and Z accordingly, and then adding on the position, or the origin of the transform. And you'll see if I open the output and run this editor script here, we get the exact same value, of course, because that is just a matrix multiplication written out by hand. And a quick note here, you'll see that I do 1 times the character position, and that's just because formally for a matrix by vector multiplication, the number of columns must be equal. So if it's a matrix 3 by 4, 3 rows by 4 columns, then you would need to multiply it by a vector 4. And because usually we want to multiply vector 3s, we actually just tack on a 1, so it becomes whatever the vector 3 is as a vector 4, with 1 as the 4th component. And then when the matrix multiplication is done, it works out that it just becomes 1 times the 4th column, which in the case of a Transform3D is the position, or the origin. So hopefully I've succeeded in communicating all this to you. Probably don't worry if you didn't fully understand this right off the bat. This is a pretty complex topic, but hopefully I at least gave you a general idea how Transform3Ds and matrices work, and hopefully you at least generally understand. And if you don't, feel free to ask questions in the comments. I'll do my best to answer them. And in terms of further learning, I would definitely recommend another YouTuber, 3Blue1Brown, you might have heard of. He has a really excellent series called The Essence of Linear Algebra, and he has a lot more visualizations and explanations about matrices and vectors, if this didn't make it click for you. And yeah, hopefully you enjoyed the video. I was originally going to release this as part of an FPS controller tutorial, but I realized this is a complex topic of its own, so I decided to split it into its own video and fully explain it for anyone who's interested in learning it, and then keep the FPS controller tutorial stuff within that tutorial to not bog that down with too much information. So yeah, look out for that. That is coming out soon, and be sure to subscribe for that, and thank you for watching. I hope you enjoyed the video.